column space, row space, the range, and all of these concepts, which often they are equivalent. So some material that we see on chapter 3, we observe it also on chapter 5 of the textbook, but probably with a more generalized approach. And now, let's see, for example, let's observe one example, which we define first, assuming that we have a matrix A, which is 1, 5, 1, wait a second, yes, okay, we have news, 2, 1 minus 1, 0, lambda 1, and this is the vector, this is the A, x is the vector which is x, y, z, and B is another vector, 2, 7, mu. Now, these two constants, so here, the lambda and mu, they are constants, okay, so they can be any number. And the question is, let's see for which lambda the system has unique solution. So here we have the first question. For which value of lambda does the system have a unique solution? So how can we check whether a system has unique solution or not? So which properties can be satisfied or have to be satisfied in order to have this?
There are multiple ones. It has to have an inverse. It needs to have only the trivial solution to the homogeneous equation.
Yes, so here we can say that A inverse exists. Okay, so A inverse exists. So let's try to determine what is but when does the A inverse exist?
When determinant of A is different than 0.
That's correct, okay. So let's try to identify what is the determinant of A. So how can
we take a pivot row. It's better if we choose the first one because it has a 0 and the other numbers are relatively small.
Yes, and then minus 2. This is 5 lambda 1 1. I agree with what you said. So what we get here, we get 1 plus lambda. This is the determinant of this little matrix. What about here? This is 5 minus lambda, right?
Times minus 2.
Yes. And then what is this equal to? This is
3 lambda minus 9.
3 lambda minus 9. And we can write it right away. Lambda minus 9. Let's equal this to 0. So in case lambda is equal to 3, so this is equal to 3 times lambda minus 3, this is equal to 0. So what can you say if lambda is equal to 3?
There's no solution.
Well, there's no unique solution, I believe. So if lambda is equal to 3, then we have the determinant of A, this is equal to 0. In fact, when the determinant of A is equal to 0, we cannot directly say whether we have a solution or not. As a reminder, most probably you already remember, when determinant is equal to 0, we could have no solution, okay, or infinite number of solutions. Whenever determinant of A is different from 0, we have the third option, which could be only, sorry, it's different from 0, then we have one solution or unique solution. So if lambda is 3, determinant is 0, then we have either one of these two. But how can we decide which one? How would you answer this?
We can try to find the value of mu.
Yes, I mean, to choose between these two, to choose between these two options, whether no solution or infinite, between,
Professor,
we have to look at the B.
Professor,
Yes,
we want a unique solution. Does this mean that lambda should only be different than 3?
yes, in this case, yes. In order to, so,
Different than 3, we have a unique solution, and that's all.
yes. So this is what we have.
But lambda is a constant. We should try to find the value. We cannot just say different from 3.
Any number different than 3.
Yes, but we are apparently we have a singularity or an unaccepted point. Okay, so the answer is this. But I was trying to clarify a little further. The one of you that said that if the determinant is 0, then we have no solution. We cannot directly say that. In this case, we have either this or this. But the answer to our existing question, for which lambda do we have a unique solution? This is the answer. So lambda should be different from 3. So if we have the, let's say here we have the lambda, this is 1, 2, 3, then we have to exclude only this point. We exclude this point, and then all the values of lambda are good. Okay? Only there we have a problem. Now, this is the first part, and now we can ask the other question: for which mu system has no solution? For which mu the system has no solution? How are we going to do this? So whenever
We
we
build the augmented matrix and try to solve it.
say it again, we try to do augmented matrix, right?
Yes.
Okay. 1 minus 1, 1. And here we have 2, 7 mu. 2, 7 mu. Now, we said that if lambda is different than 0, we have a unique solution. We don't want this case. We have to have no solution, which means that what is lambda?
3.
Should be 3.
Yes, that's true. That's true. In order to step in this domain or in this approach, in this what we are saying, lambda has to be equal to 3. That's true. And then we have to solve the system, and in order for the system to have no solution, what should we get? When does a system have no solution?
If the rank of the augmented matrix is bigger than the rank of the matrix itself, a reduced echelon form.
That's correct. One way is to report it in this form. So if we get from the reduced row echelon form, the last row is 0, 0, 0, 1, then we have no solution. Or similarly, as you said that the rank of A is smaller than the rank of AB, right?
Yes.
So it's either one of these two. So if we try to get the reduced row echelon form, we can, let me see, I believe we can use this one as a leading one. And with this one as a leading one, we do the following. We have the row 2 minus 5 row 1. And then we can do row 3 minus row 1. Okay? Because we make the relevant zeros. And if we follow this one a couple of times, in the end, we're going to get 1, 2, 0, 2. Actually, this is the first row, it does not change. And then we have 0, 3 minus 1, 0, 3, minus 1, 1. And then we have 0, 0, 0, mu minus 1. So,
Professor,
yes,
I didn't end up with that.
say it again.
Why is the 3 over there? I got -9.
Yes, I skipped one step. That's true. In the first step, we should get -9, but I followed with I did 2 steps at once. Wait a second. Now I want to use some part of the board problem. Yeah. If you want, we can follow also from the first step. Let's say you are right. This is 5 minus 5, 0. Then we get 1 minus 10. This is -9. Then we have 3 minus 0. This is it? Did you get 3 here? 7 minus 3. And then we have 1 minus 1, 0, minus 1, minus 2, minus 3. And we have here 1 again. And mu minus 2. We get here mu minus 2. And the next step is we can divide this by 3. Okay? If we divide this by 3, or can we divide this by -3?
Yes, -3 would be better.
Okay, if we divide by -3, we get here 1. Okay, then here we get -1. And here we get 3. So if we have this, in this case, in order to make this 0, what can we do here? Row 3 star, the new value of row 3 would be row 3 plus row 2. Okay, and then we get 1, 2, 0, 2. This is 0, 3, minus 1, 1. This is 0, 0, 0. What is the rest? Mu minus 1. Okay, so this is the reduced row form. It's not it's row echelon form. It's not the completely reduced one, because we can simplify this a little further. But I think this is enough for us to try to answer this question: for which mu the system has no solution. So in order to have
Different than 1.
mu
Different than 1. Okay, mu minus 1 is different than 0, which means that mu is different than 1.
yes.
So in order for the system to have no solution, we should have lambda equal to 3 and mu different than 1.
Yes. So let's see here. We need the lambda should be equal to 3, and the mu is different than 1. Okay. So let's put here mu. This is mu, and this is equal to 1. So let's assume that this is like a Cartesian coordinate system, x and y. But here we put lambda and mu, and let's draw a line here which corresponds to mu equal to 1. Okay. And let's see what we observe here. It looks like, first of all, let's leave this point empty. So I just want to have a look one final time. So when lambda, we have a unique solution everywhere except this value. But having lambda equal to 3, we can draw a line. So this is the problematic line. This is the problematic line for lambda equal to 3 for all possible values of mu, because at that specific value we have either one of these two. Okay. Now, if mu is different from 1, where is mu different from 1? It's actually everywhere except this line. Okay. Or let's do it like this. What happens if mu is equal to 1? If mu is
Any
equal to
solutions?
1, that's true. So lambda 3, mu 1, it is this point here. At this point, right here, we have infinite number of solutions. Right here, just at this point. And then, if we have lambda equal to 3, lambda is equal to 3, and mu different from 1, we have no solution. Okay, so I believe we are here. I wish I had a red color here, but no, I don't have a different color for the... So, lambda equal to 3, and mu different from 1. So let's draw it like this. Let's draw a double line or a triple line. So this triple line, this corresponds to, wait a second, mu different from 1, we have no solution. So here, so the problem that we have to analyze is what happens in this line where mu is equal to 3. So I think we have answered everything. So we have a unique solution everywhere. Wait a second, we have a unique solution. Where did we have a unique solution? Excluding the other 3, right? Okay. So we can plot all this domain, which we do it here in dots. We have here a unique solution. Okay. Everywhere except the 3, we have a unique solution. We have no solution if we stay here. We have an infinite number of solutions right here. Okay. Is it clear?
Yes.
Okay. So let's try to identify null space of B. What is the null space of B? How can we find it? So this is 4 by 3, and normally this would be n, sorry, this is B, which is 4 by 3, times x, which would be 3 by 1. This would be equal to 0, which is also 4 by 1, okay? So we're trying to identify 3 numbers, or a triplet of numbers which can satisfy this condition. So what we need to do for that, we need to get the reduced row echelon form, and to make it 0, we have here 4 minus 4, 0, 1 minus 4 minus 3, 2 minus 12, minus 10, 0, so we do the third row plus twice the first row. We get here 3, 5 plus twice plus 6, this makes this 11. And then we have row 3 minus 3 times row 1, this is 0, minus 5 minus 8, 1 minus 9 minus 8, okay? And then we could put here 1, 1, 3. We can put row 2 here and divide by minus 8. We can do this like this. And then this is 0 minus 3 minus 10, 0, 3, 11. Then we can use, this was a leading one, this is another leading one. So if we use this leading one, how can we modify, this is 0, 1, 1. How do we make it 0? We add 3 times row 2. So this is 0, 0. And this is minus 10, plus 3, this is minus 7. And here we get this one, minus 3 times row 2, we make this 0. 11 minus 3, we get 8. And this remains 1, 1, 3. So, what do you see here in the last 2 rows? We can modify row 3, dividing by minus 7, okay? And row 4, we can divide by 8. So, if we do this, we can obtain here 1, 1. So, row 3 and row 4, they look like they are equivalent. So, we can simply do the next step. We can do row 4 minus row 3. What would we get then?
0.
That's 0. Thank you. And now, what we observe is that we have these leading ones, okay? If this is the case, this is all zeros. It is easy for us to produce here as the next step. Zero, 0, 0. Then we can do row 2 minus row 3. We get 0, 1, 0. And if you look at this carefully, it is very easy for us to obtain the following. Okay. Now the question is, we have to multiply this one by x1, x2, x3, and this would be equal to what? So for which values of x1, x2, and x3 do we get zeros here?
Well, x1 should be equal to 0. I think all of them should be equal to 0. No other solution.
That's correct. So the null space would be, what is the null space would be? It's a triplet of numbers x1, x2, and x3. All of them 0, 0, 0. So sorry, I can write it better here. x1, x2, and x3. This would be equal to 0, 0, 0. So the null space would be, it is it's a set of vectors. So we go here from a point 0 to another 0. Okay? For sure, this is not two-dimensional. Let's say the range. What is the range of, what is this range? Is it R4 or R3?
R3, because we only have 3 variables.
Actually, what did we say? The range is a linear combination of the columns, right? Because we add the columns with each other. The columns, how many numbers do we have for the columns?
4.
4. So the range of matrix A is R4. The null space or the domain is 3. Why? Because the vectors X have triplets. So I believe that the range here, this is R4, but whichever way R4 we can represent, this is going to be from 0 to 0. So the null space of B is equal to what? Null space of B, we can also report it like this. You can have the 0 vector. And this is a vector space in itself, because this includes a 0. If we add the zeros together, we still get a 0. If we multiply the 0 with a constant, we are still good. Negative vector 0 is still 0. So we can have V and minus V. So this is the null space of this matrix. Okay. Now, let's come up with a different example. So let's have a matrix A1, which is, give me 2 numbers. Give me a couple of numbers. Someone, give me a couple of numbers. So if we put here 3, 5, can you know, we said that we have, let this A1 be like this, okay? Let this be a vector, a column. We have discussed about the range, and we said, what was the range of a matrix? It was a linear combination of the columns, right? So can you give me a vector which is in the range of A1? So get me a vector such that the vector V is in a range of A. What should this vector look like?
3t plus 5s, where t and s are full numbers.
Yes, so vector V would be something like this. Actually, 210, no, 610. 610. Or another vector V can be minus 3 minus 5, right? And then, okay, fine, we learned this. As you said, we can multiply 3s, 5s, that's true. But this is a couple of one with a comma. Now, let's assume we have a matrix A2, which looks like this, 3, 5, and let's put here 6, 10. So I compose a new matrix using the previous vector and the range of this. Okay, so what was the range of the first column? It was this. Okay. How does this matrix look to you? What is the determinant of this matrix?
0.
0. That's true. So here we have the determinant of A2 is equal to 0. Let's have another A2, okay, which is equal to 3, 5, and let's get the other one. Well, let's write it like this, 3s and 5s. Would you agree? Ne mund të shkruanin këtu edhe minus 3 minus 5. Okay, but let's keep it general. So what is the determinant of A2 now?
It's 0 again.
0.
It's 0 again. Okay, so we have the determinant of A2 is equal to 0. Okay, so then can you produce a vector W that is not in the range of A? Find W such that W is not in the range of A.
3s, 6s.
Yes, you said 3s and 6s, right? Okay, that's true. We could also do the following. You can have the following. You can say 3s, 5s plus k, okay? Where k is different from 0. Would you agree?
Yes.
Just give me one short sentence. A second. Hello. Oh. Okay, so how can you make up vectors which are not in the range of some other vectors? Okay, or which means that a vector which is not linearly dependent with what we had before. So here we have 3, 5, right? A vector W could look like the following. This would look like 3 times 3, 9, 5 times 3, 15, plus 1. Okay, this is it. So you can use this one. Right? Or you can do any other trick. So in this case, let's assume that we can come up with a matrix A3, which is equal to 3, 5, and let's pick a number here, 9, 16. Okay? 9, 16. What is the determinant of A3 here?
3. 48 minus 45 equals 3.
Is 3, which is different from 0. Okay, now let me ask you this. What is the null space of A2? Let's find null space of A2. So I'm asking this. I can ask also something, what could be a simpler question than this? A simpler question than this would be the following. What is the null space of A3? Can you answer this straight right away? What is the null space of A3?
Would be the trivial solution.
Of course. That's it. Why is this the case? Because we're looking for the solution x such that A3 times x, this would be equal to 0. Okay? And we know that since, let me write it like this, since determinant of A3 is different than 0, then we can say that A inverse exists. Okay, if A inverse exists, then we can say that this has only the trivial solution. So x is equal to 0. So it looks like if we want to find the null space of a matrix that has a determinant different from 0, we can immediately find, this is a very easy question. Okay, you come to an exam, you're asked to find the null space, you look at the determinant is different from 0, you get the 0, you got it. Okay, it's very easy. Why? Because these vectors are linearly independent. There is no way that we can produce a 0 by combining these with simple coefficients. Now imagine for a moment if we had this. If we had this matrix, 3, 5, and minus 3, minus 5, right? Minus 3, minus 5. And we need to find some vectors, x1, x2, such that this is 0, 0. Now, what is this matrix? This matrix is A2, right? Because A2 is expressed as the first column and the range of. Would you agree with this? So, what would be a solution? Can you give one solution here which satisfies this equation?
1, 1.
That's true. So here, one possible solution is x1, x2. This is equal to 1, 1. Okay? And then we can also come up with a different, let me think for a moment. Any other solution?
It will have infinite solutions.
Yes, 2, 2 is also a solution, right?
Yeah.
3, 3 is another solution. Minus 5 is a solution. I believe you agree on this. So it looks like we have an infinite number of solutions, but let's try to identify those. How can we identify those?
The linear combination of 1, 1 with itself.
Yes. So a constant times 1, 1. What is a constant times 1, 1?
Is it a line?
It's a line. So this is 1, 1. Then 2, 2 was also a solution, right? 2, 2. So we get this point, we get this point, we get 3, 3, we get minus 1, minus 1, minus 2, minus 2. So it looks like we might get a solution which is going to look like this, okay? If we want to check this carefully, we can do the following. What was A2? A2, let's pick one. Let's pick this one. 3, 5, 6, 10. They're going to be very similar. 3, 5, 6, 10. Let's do the, this is equal to what? 0, 0. So we draw the augmented matrix. Then from here, we divide by 3. We get here 1, 2, 0, 0. This is 5, 10 again. And then we do the second row minus, wait a second, is this true? No, I think that's true, yeah. Then we have the following. How can we make 0 here? Row 2 minus 5, row 1, right? Yes. Then from here, we get here 1, 2, 0, 0, 0, 0. Wait a second. So I think, yeah. Sorry. Here we use this matrix. Now here we are using this. So probably the solution is going to look a little different. So what do you observe from here? From this reduced row echelon form of this problem, let me steal a little bit, let me get some space. So from here we observe that we have x plus 2y is equal to 0, right? So what is y here? What is y? Minus 1 over 2.
Minus x over 2.
Yes. Now, we drew this line. How would we get this line? We would get this if we had here 3, 5, because we got this number from this other matrix, minus 3, minus 5, right? Minus 3, minus 5, and this would be 0, 0. So this matrix and this one, they are both A2 style, A2 category, right? The first column times the multiple. And then we can divide the first row by 3. We get 1 minus 1, 0, 0. And here we have, it is easy for us to obtain here 0, 0. Do you agree with this?
Yes.
Then what do we read from the first equation? We get x minus y, this is equal to 0. So y is equal to x. So what is this equation y is equal to x? Is this. And how many possible solutions do we have? This is an infinite number of solutions. What about for this other matrix, 3, 6, 5, 10? The solution, or the null space, it is y is equal to minus 1 over 2x. How do we do that? This has a negative slope, okay, so the best case scenario, we know it is the minus 1 slope, right? It's a slope which is going to look like this, right? But we have a slope which is half of that, which is somewhere, so y, or let's do it like this. Let's say x is equal to minus 2. What is y? If x is minus 2, what is y? It's 1. That's true.
1.
Can you give me another point? X is 0. What is y?
0.
Is 0. We can also assign x is equal to 2, y is equal to minus 1. So 2 minus 1, we get a line somewhere here. So the slope is 1 over 2. So then the solution is going to look like this. This is the line which I can draw, which actually is right here. So these are the null spaces of the matrix which was composed by the vector, the original vector, which is 3, 5, and then the next columns, they were in the range of this one, and as long as the new vectors are in the range of the previous, of one of the columns, then all we get is this. Determinant is equal to 0. If the determinant is, wait a second, if the determinant is equal to 0, we might expect an infinite number of solutions. The problem is, when the new vector is 1, you multiply 3, 5 by 2, then you just change one number, okay? You play the trick, you break the symmetry, okay? So you have a vector 3 times 2, but then you shift it by one number, which you can use this one. Sometimes I ask this in the exams. I say, produce for me a matrix which has determinant different from 0. I mean, students, I've asked this one in previous years. Students, they started complaining, Professor, how can we find out a matrix which has 3 by 3 matrix where the determinant is different from 0? They write down some numbers randomly and start calculating the determinant, you know, which takes a lot of time. But a simpler way is you make a few rows or a few columns, you make them linearly dependent, and then break down the linear dependence by adding these constants, okay, where k is equal from 0. So now I think that we obtained what was this. This was y is equal to x. This was the null space of this matrix. This is another matrix which looks like very much like this, but maybe I have to show that this has this solution, minus 1 over 2. Okay, so this is how we try to identify the null spaces of matrices. And with this example, I believe it's a little more clear how or what is the role of the inverse of a matrix or the existence of the inverse with the possibility of having an null space, which is, wait a second. So here, what did you say? We said the null space of A3 is 0. So what is the null space of A3? It's going to be just this origin. So for A3, the null space of A3, well, I think we wrote it here. Anyway, it's clarified here, but I will show this. This is the null space of A3. Why? Because A3 has this determinant different from 0. Do you have any question?
No.
Okay. So the quiz, we're going to have it on Friday, and we set the time, something like around 5. Okay, so if you have no...
Professor, I have a question related to previous topics.
Yes. What is the question?
For example, let's assume that the two parametric equations are given for a line, and we want to find the parametric equation of the plane, assuming they are not skew. Can we just add the positional vectors of them, the directional vectors?
Wait a second. You said that you have a plane. Can you repeat it again? You have a...
Yeah. No, I said, suppose there are given two parametric equations of two lines.
Okay, line 1 and line 2, yes. Yes, we are given...
Yes, and we want to find the plane equation. Assuming they are not skew and they intersect at a point, can we just add their directional vectors?
I don't know. Let's see. So you have two lines, line 1 and line 2, and you want to find a plane which is defined by these two lines, right?
Yes.
Okay. Well, my first answer is that I don't know. Let's try to figure this out. So we have line 1, and give me one parametric equation.
For example, let's take one line that passes from the origin. For example, 1, 2, 3 times t.
Yes. So, but line 1 would have an equation which looks like this: y is equal to 3x plus 2, right?
Yes.
Okay. Then let's have another line 2, which is going to look like y is equal. Give me a couple of numbers.
X plus 3.
X plus 3, okay. And now we want to determine, or we want to find the equation of a plane P1, which is defined by these two lines. Now, let me ask you, do you have any suggestion? What can we do?
My question was more about if we have the parametric equation of lines.
Yes. And okay.
So in the vector form.
So you want to have, so actually how would the parametric equation of this line look like? Is that what we mean with parametric equation?
Yes. And we just say 1, 3 times x plus 0, 2.
Let me think. Oh yeah, okay, so you mean this. You mean that we have line 1, which is, okay. You say line 1 is defined as P1 plus S times V. And how would this be written in this form? What is P1? 0, 2, right?
Yes.
And plus what?
Plus 1, 3 times x. X times 1. 3.
Yes. And then we have another line L2, which can be written. I'm trying to think this problem, okay? I don't know yet how we can solve this. But this is equal to, we have here x, y. This is equal to x is 1, and the y is x plus 3, right? No.
X1 is 3. Yeah, no, it's x plus 3.
Wait a second. Is it correct? It looks correct to me.
Yes.
Yes.
It's 0, 3 plus t times 1, 1.
1, 1, yeah. Okay.
So in this case, can we say just the plane equation is, for example, 0, 2 plus s times 1, 3 plus t times 1, 1.
I have to think about this. Would you agree? Do you think that this is a good solution? But this is the correct solution? So you are suggesting that
I think since I said in the beginning that we assume they aren't Q, I think yes. I don't know.
let me try to wait a second.
Since there is a directional vector for the first line, and now we just get the second one, the second directional vector.
You know, I think you're right. But what? Let's use it. Why don't you use? I think I believe that's correct. So we're saying that the plane P1 would be equal to. Then you're saying this 0, 2 plus 0, 3 plus s times 1, 3, right? Plus t
Yes.
times 1, 1. In fact, the equation of a plane, it does look like this, which means that we have two directions, orthogonal, not orthogonal, sorry, two directions which are not linearly dependent. So we should not have a direction 1, 3 and then another direction 2, 6. That would be unaccepted, not satisfactory. But let me think about this problem. Is there any student in the class that has a comment on this? Does this look like a good solution? You know, I think, let me answer also this question. Does this line pass through the origin?
No.
No, it doesn't.
No. Where does this pass? Y is equal to, let's set x is equal to 0, and this is going to be equal to 2. This is one point. And the other point, we can set this, let's set x1 and y, or let's set x minus 1. What is y? Minus 1, right? If x is minus 1, I think I'm correct, right? Minus 1. So we get these 2 points, and we have this. In fact, this problem is this is pretty obvious for one reason, because we have two vectors, two directions. So my first answer would be this. This is always true. No one in the world can say that this is not true, because the space that we are using, is two-dimensional. And if we have two vectors that are not linearly dependent with respect to each other, this is always true. Okay. This plane is going to define this too. Okay. What could make this problem a little more challenging would be if we had a line that looked like this. Imagine for a moment the following. Your question is a very good one. Okay, we'll try to provide a little more insight into this. Meanwhile, I think we need this. This is what we are talking right now. But I want to make one thing clear, and I thank you for your attention. Imagine if we had a line that looked like this. Line 1, which would be 0, 1, minus 1, minus 3, okay, plus s 2, 3, minus 4, okay. And line 2, this could be written as 2 minus 1, 1, plus t, 1 minus 1, 3, okay. Now, this problem that you proposed, I think this would be the correct answer for 100 reasons, where the simplest one would be that you are in R squared. First of all, L1 is a subset of what? Let's see this. L1, we're looking at this part of the board. L1, it is R squared, right? Why? We have a couple of numbers, a pair of numbers. So this makes it R2, which means that if it is R, it's only one number. If it is R2, we get 2. Then we have also L2, which is also in R2. Then what is plane? The plane. The plane which is going to include line 1 and line 2. This is also R squared, right? But the thing is that with two vectors, you can cover the whole R squared. It's not that you are looking for a specific region in R squared. Okay? Now, a more generalized version, which means that this is correct, as you suggested. Now let's come to this other case. We have line L1 here, L2 here, and we have to figure out what is a plane where these two lines pass. This is a little more difficult problem because
we can prove that they are not skew. I think we can just do the same.
You think so?
That's what I was aiming for. That's what I was aiming for, to prove this in a generalized form, as long as we know they are not skew.
If you are saying this, if L1 and L2 intersect, right?
Yes.
Then you are saying that the equation of line 1 plus the equation of line 2, let me write it like this. This is the equation of a plane, right?
Yes, that's what I was asking.
Let me think about this one for a moment. So we have a plane that is passing through some point, and we have a line, sorry, it's a line in three-dimensional space. We have another line in three-dimensional space, and we try to identify these. Wait a second, I believe, I'm not sure actually, I don't know. Or I can derive it in a different way, and then I can prove whether your statement is true or not. But what if I approach something from a little to somewhat generalized approach? What is the equation for plane? Would you agree that the equation for plane is written as some numbers, you know, that we have like C1x plus C2y plus C3z. This is equal to D. And the plane is equal to n times x. This is equal to D. This is the equation of the plane. Would you agree?
Yes.
Where n, as a representative example, assume a plane P5. It's not the P we're working for. P5 would be 3x minus 2y plus z. This is equal to 4. This is a plane. This looks like a plane we solved in the second session of this class today. And now, one approach is this. How can I find the normal vector? How can I find n? So for these two things, which you provided to me, which are in R cubed, the most essential part is this. What is that? Now, how can we find it? One thing that we can do is the following. Let's try to identify a vector along L1, okay? And then we find another vector along L2 and take the cross product. How does this look? Can I erase this part for a moment?
Yes.
Okay. Then let's try to identify also this one. Okay, this was again the same. I believe solving this one is more important than solving this with two vectors in two-dimensional space, which anything is possible. But now, let's assume L1. Let's find a point in L1.
Professor, jemi aq të lodhur sa unë s'po kuptoja asnjë gjë për vendin.
Sure, we can do it like this. These are your questions. I can answer these, and we're going to share the recording. Okay, so we can have a look at this recording later with a more clear mind, I believe. But if you have anything which is not clear, I can answer. With the online version, we always have the opportunity to go back to the recordings and stop it and listen it twice. So you can leave if you want to leave. You can go because this is way beyond the class time. Okay, we are good. So you are yeah. Probably you could be. There is a probability. There is a non-zero probability that you are in more comfortable setting than me right now. Maybe I'm right. So let's try to solve this problem, okay? Because I cannot really visualize whether this is true. It could be true, but let's see. Let's find a point in L1 when S is 1. So what would be this point? This point, can you answer this for me? Would you agree? So I just added this line here. I did 0 plus 2, it's 2. 1 plus 3, it's 4. And would you agree this looks like a point in line L1? And another point in line
Yes.
L1, let's set S is equal to minus 1. Let's use minus 1. S is equal to minus 1. We put a comma here, and what should we get? Minus 2, minus 2, then what is it? 1. Is this right? Okay. So this is 1 point, this is 1 point. Now, we need to define a vector, which is along L1. How can you define a vector? To define a vector, I'm going to erase this one, so you can have a closed loop. So, if this is a line, let's assume that this is a line, okay? And I'm defining a point right here. And then I'm defining another point, okay? Let this be point 1, point 2. How can you determine a vector along this line? We can assume that this is point P1 and point P2. What is a vector?
You can find the midpoint.
The difference.
Right? We can find the difference.
Yes.
Why is there the difference? Because we know that if we do P1 minus P2, what will P2 be? P2 is going to point downwards, right? And let me take this out. If this is P2 and this is still P1, how simpli din vektorave? Marrim vektorin e parë, te koka e vektorit parë, vendosim fundin e vektorit tjetër, nëse kemi më shumë, i vendosim shumë apo jo. Shihni edhe vektorat. Jemi çfarë këto pjesa? We know how to add vectors. We don't have so many, we have just 2, which is good. So P1 minus P2, so any 2 points in a line would give us this line. Okay? We could also do P2 minus P1, we'll get the negative. We'll get this other vector pointing this other way, right? So if we believe that this is true, then the vector which is going to point this way, I can write it in here as, let's subtract P1 minus P2. We get 2 minus minus 2, this is 4. 4 minus minus 2, this is 6. Minus 7 minus 1, minus 8. Okay, we found it. Okay, then this is line 1. Let's find for line 2. For line 2, let's do this when S is equal to what? Sorry, T. We have T here. And by the way, this is, let me write it like this. This is P1 minus P2, which is a vector V. Okay, and this vector V is pointing along the line L1. Then L2, when T is equal to 1, let's see what we get. When T is equal to 1, we have a point along L2 which is 2 plus 1, 3, minus 1, minus 1, minus 2, and 1 plus 3, 4. Another point, shall we set T? We can put T minus 1. Let's try to keep it simple. Sorry, this is S1, S minus 1. T is equal to minus 1, and we have here 2 minus 1, 1, minus 1 plus 1, 0, and 1 minus 3, minus 2. Is this correct? These are points along the L2, and this is a vector which is going to tell us the direction along where the L2 is going. So let's add these. Sorry, we subtract these. 3 minus 1, 2, minus 2 minus 0, minus 2, 4 minus minus 2, we get 6. Okay? So what is this? This is point P3 minus point P4, and this is equal to a vector W. So what did we get? We have 2 directions which are pointing, which are now these 2 vectors. Are they on the plane that we are looking for? Yes, they are, right? Yes, they are.
Yes,
so
they
now, what I'm still looking for, I'm searching for N. How can we find N? It is easy. N is going to be equal to, or at least the direction we're going to find it correctly. N, we can write this one as V cross W. Would you agree with this? So we have a plane, and we have a plane that looks like this. I have 2 vectors, which is, one is pointing like this, one is pointing this way. Anyway, I have the board, I can do the same, but this is something not orthogonal. What is the best angle you can see these lines? And then we take the cross product of these 2 vectors on this one, and you get this normal component. So let's do this. Let's say the cross product. Here we have I, j, and k, and vector v, it is 4, 6 minus 8, 4, 6, minus 8, and the other vector is 2 minus 2, 6, 2 minus 2, 6. And then we get for I, we get the, what is this? What should I write here? 6 times 6, 36, minus 16, no, minus 16, 20, yes, we get 20, minus j times, so this is how we do the cross product, j, this is 4 times 6 is 20, 24, plus 6,
Plus 16.
40 maybe, plus k times minus 8, minus 12, minus 20. So we found n, okay, n is good. So what is n? N is 20 minus 40 minus 20. N is equal, is a vector. Actually, I can draw it better this way. So this is going to be 20 minus 40 and minus 20. Okay, now we know n. We don't need to know what is x, but I need a point d. I need a point d, which is in the plane. Okay, let me think for a moment. So we should satisfy that d. But wait for a second. So we get yeah. So this is n times x would be equal to. Wait a second. How can you find d? The d is, yeah, I think d can be any point, but you know, can you? So we found the n. Can you try to find what is d? Why don't we leave this as a homework? If we cannot solve it, we can.
Okay.
Okay.
That's okay.
But I believe this is a good approach how to solve this one. Okay. So because all we need to find is this value. Any other question?
No.
Okay. So if there is no more question, actually I have to look at this video and I can provide the answer in written, and I can upload this on Google Classroom. In case you cannot solve this up to the final points, if you don't solve it completely. Okay, if you have no more questions, then we can stop it here, and I hope to see you again this Friday when we have the quiz.
Profesor, po limitowi si dojet.
What, say it again?
Limitowi si dojet.
Midterm. Oh, I'm going to announce this one, okay? I have to look at the regulation. We just received today the regulation by our administration, but I didn't have time to read it carefully because I was a little busy. So I'm going to look at the details over there, but it could be something, it's going to be online, okay? So it's going to be a combination of multiple choice and analytical solutions where you have to show all your work. But more details, give me a couple of days and I'm going to tell you.
Okay.
But do expect multiple choice questions, okay?
Okay.